that's why you're confused, like, well, how did you know that you're supposed to do this line?
Yeah.
So perhaps we should talk about that today.
Yeah, I just I'm thinking that, yeah.
So you're saying it's good we have the workshop? Yeah, okay. Thanks, I feel appreciated. That's the way I'm reading it.
But Robert Jane started it like last week, and now that he's going, no, it's not starting.
What is it, the limits of functions?
Yeah. Because now you just focus on
The definition of limit.
Yes, it does.
Yeah, well,
That's what it did, Shaba, and the examples maybe provided.
yeah.
That's-
So examples made us more confused. You know how examples are supposed to clear things up and you're confused? Yeah.
That's why I have like
What was confusing about it is I mean, maybe we'll get there specifically, but it was like the way it was presented or the specific examples?
And actually, when you just take up our book.
So while I erase, I'll just chat a little bit. So, I mean, one thing we could do today is we could do like a post-mortem on the test. I don't know if I like truly recommend that, just because I don't think you all have a memo yet for it, right? He hasn't released the memo yet. I think that'll come after we finish marking. So probably what's most useful for all of you, unless you desperately want to ask questions about the test, is like ask those questions individually. And then once the memo's out, everyone can have a chance to look at it, and then in a later workshop we can talk about all that. Then like we did do all this stuff on like kind of topology of R, in other words, open and closed sets. So we can
brush that. You know?
We can do some of that, but to be completely frank with you, it's like not central to the course.
Yeah.
You need to know what a closed set is, you need to know what an open set is, and you need to be able to kind of like look at an example of some closed sets and some open sets and just say like, yes, no, maybe, well not maybe, but like neither, because there are some that are neither, or both, there are some that are both. So like, I don't want to say let's not do that at all, but typically the sort of the purpose of the course is to get on to this like continuous functions, limits of functions, things like that. So I'm totally happy to go right there if
Truthfully, I actually started getting lost with RA as soon as the word topology came out of my lecture.
well, it's like, what is topology? It's just the study of open and closed sets in some sense.
Then there is another question like, what is a topology?
What is a topology?
Is it? Are we supposed to know that? So sorry.
I'm sure you're not. Maybe. But, I mean...
Okay, so this is what we did today.
Do you mind if I actually just take a look? Maybe
Yes.
that will be...
Sorry. It starts here.
So this was today's lecture.
Yeah, it starts here and then...
Oh, I was expecting this one.
And then this and this.
Was figured backwards.
Yeah,
Okay.
yeah, right.
Okay, so they're giving you like an example of a weird function. They want to give you the definition of the limit. And this function is just
Yeah,
a compact plus phenomenon.
He was explaining why, you know how previously we defined continuity as long as you don't have to lift your insole.
Yes.
So and he was just like, then you see with irrationals at the ends as well as rational at the ends. And then he then defined what is a limit, and then he provided examples, which is
So
made
did he
everyone
just
confused.
he covered continuity and limiter at the same time, or he first covered the limits?
I don't know,
You'll have to
was
do-
this continuity? I think it was just limits to
Yeah,
it.
just limits there. We'll get to continuity in the future.
Yeah.
And then we'll do uniform continuity, which is going to make you all upset, and then we're going to make it
Dude,
fine.
okay, guys,
Okay, cool. So it sounds like we should just start by talking about the definition of limit and do some examples. Is that kind of fair? Yeah.
You know what? I think when it that is we talk about continuity because from limits, continuity follows from limits. I think it's easy to understand continuity from limits.
Exactly.
Then after that, we talk about uniform continuity. Just give us the idea of what is happening there, you know?
what is happening there.
In uniform continuity, before we get scared.
I feel that we probably shouldn't fully go there, but just like very briefly, the point is to do some useful things, just the basic definition of continuity is not enough. So, look, why don't you and I chat towards the end? Just because I'll have to think.
Already overwhelmed, so
Right, and to say everything I want to say is going to require just sort of reviewing the definition of limits anyways, but very briefly I could just tell you, like, the definition of continuity is going to be like we defined it in Man 1000, which is something like, you know, the limit as you approach that point is equal to the function at that point in some sense. But that's going to be true. What we mean by that limit existing means that there's like some delta, or equivalently on the sequence side, it's corresponding to some capital N that makes something true. And that delta is going to, or that capital N is going to be for each point in the domain. So there'll be a different one for each point. Uniform continuity picks one for all the points. That works for every single point, so for all x's in the domain. And the reason why you would care about that at all is we just find that the normal definition of continuity just doesn't allow us to do some useful things that we want to do. So for example, you might want to do something like, I make a sequence of functions that converges to a function. And like if each of the functions in the sequence is continuous, maybe I want the function that it converges to be continuous.
Okay.
Why would you do that? Well, like maybe something to do with Taylor series or something like that. But anyway, we're not there yet.
Okay.
But the point is, long story short, continuity is just not good enough to do some things that are useful that we've actually seen in the past, but we're looking at in a new light. But okay, let's go back to limits though. Okay, so on the sequence side, we all remembered that we just had this idea that if n goes to L, we're going to say that for all epsilon greater than 0, there exists a capital N such that exactly it's going to imply that, what did I call it? An minus L is less than epsilon, right? And what we were just saying with this definition had like a pretty intuitive picture, though it was a bit nasty to learn at first. It was just saying like, if we go far enough along the sequence, an is always close to L. Yeah, close to L. And I could say that in a lot of different words. I could say as close as we like or something like that, but that's the picture, okay? So that's like kind of one. So what's the function definition? Well, we could start by writing in words what we want. We had this idea that like, basically if I draw this, okay, I want to say something like, I want something like x close to A implies f of x close to L. Do we kind of agree on that? That might be what the limit means. And if we really wanted to make that clear, we're saying something like, if I pick this point A in the domain, as x is kind of getting close here, what should happen is if I have my f of x, this is my f of x, I look at this value. This would be L. Okay. And I just want f of x to be getting close to L. Okay, I've kind of defined this circularly, if that makes sense, but this is really a statement about x close to A, down here. So like x is somewhere in here. And then what must happen? F of x, in other words, the y values, must get close to L. So this is the y values, okay? And then we just kind of, in the way that we did for sequences, when we said, okay, I want to go far enough along the sequence, then the sequence AN is always close to L, that we just translated that into some really formal language and then checked that this definition reproduced everything that we wanted by saying this, okay? So we said far enough along, that was this point, there exists a capital N such that this, whenever little n is bigger than capital N, and then we said AN is always close to L, that's that part, okay? So now we just need to find the corresponding thing for this kind of sentence. X close to A means f of x is close to L. And so, well, just roughly, before we sort of write it down perfectly, like, you know what x close to A is going to mean. There's going to be something like this floating around. So this is x close to A. To A. And then f of x close to L is going to mean that we have to have this floating around, of course. Right? And really there's going to be like a implies, like, so this is going to imply that, okay? So when this happens, this has to happen, okay? And then what do we mean by close to? We mean really kind of less than some positive number, and it's just very, very traditional in the literature. There's no reason for this to matter, but they tend to give this one in the domain, remember this is talking about points in the domain, they tend to use delta, and over here they tend to use epsilon still, okay? So yeah, so we're just saying points, when you look at points close in the domain, the image of those points, in other words, the y values or the f of x values, are close to L, okay? And then we just put it together, like, carefully. You might wonder, like, sort of what order is the right way to do it and all, but if you see that if you look through it carefully, the definition that they give you really does make sense. And perhaps more importantly, we'll go through some examples and see that it reproduces what we expect it to do. So that's kind of why it's a useful definition. So we're going to sort of translate this whole thing. We say for all epsilon greater than 0, we now want there to, we want to say that for all x such that x minus a is less than delta, we want that to imply that f of x minus L is less than epsilon. Okay. Now there's a little bit more to this. They say something about like, oh, A needs to be like a limit point or like something like that, but we're not gonna, we can elaborate on that in a moment, but this is really the important part of the structure, right?
Can't we like say for all something exists like delta?
Yeah, I think I probably, sorry, I think I left out that there exists.
Such that for all.
Yes, yeah, sorry. There's definitely the exists of the delta. I need to get the order correct.
Because now it's, instead of using
and then for all x, there exists a delta. Okay, sorry.
I'm confused because this x minus a is less than delta kind of reminds me of the distance between x and a is always going to be less than some positive number delta.
Mm-hmm.
Isn't it for all delta then? Or is delta fixed? Is that why we're saying they exist?
So that little part of it is subtle. That's a reasonable question. So what really we kind of want to, I don't know what's the most convincing way to say this, but we're just saying that sorry, give me 1 second to get this right. Right, so I think I should actually just be leaving this off, and that's probably obscuring more than something. Okay, so we're really talking about the limit at the point A. And so what we really want to just say is that every time you give me an epsilon, I want to look nearby A. And what this is saying is I can make this point, this interval in the domain small enough to make this true. Okay, so we'll say that one more time. The there exists part of this statement is capturing the idea that it might not be true for all x, okay? It might be that if I go a little bit far away or something like that, you know, maybe we're too far, you know? And that really, what I want to sort of emphasize, at least in terms of, it's true that this is how the structure works, but it's also a way to help you remember the structure of this is to compare this first part with the part for the sequences. So we weren't saying that all of the the ANs were close to L, not for all the N's. We were saying that there exists some capital N such that all of the little n's past there are close to L. So perhaps what we could have rewritten this maybe to say something like, I can make x close enough to A such that this is true. It's possible to make this true. What do I mean by it being possible to make it true? I can find a delta, in particular it might be quite a small delta, that I can go close enough to A that all of the x's that are close by A will imply that f of x is close to L. So that's the reason for the there exists. I wonder if we could say, what if there was a for all?
For what?
For all delta, yeah.
That's when the
That's actually
limit doesn't exist. That's when the limit doesn't exist.
I don't think that would say the limit doesn't exist.
Because if this statement is true, then we know that the limit exists. It converges to L. So the limit is L.
Sorry, one more time?
So if this statement is true, we know that the limit as x approaches A of f at x is equal to L.
Yes.
That's true. And if the limit is not equal to L, that's why we negate this statement. And that's when we...
Oh, but that would require a lot more, right? So negating this statement, if you wanted to negate... I see what you're saying. Okay, so you're thinking, okay, what if there was a for all? That would mean I negated something, but remember you'd have a sort of a for all delta, there exists an epsilon, such that this is true, but that inequality flips, and yeah, we should actually talk about that. Maybe we'll do that in a moment once we're definitely happy with
That's
it.
when we have for all.
Okay. But let me just put this up here. So perhaps what I want to say is something like, maybe to re-summarize, like, given epsilon greater than 0, I can find a small enough interval around A such that f of x minus L is less than epsilon for all x in that interval. Okay? So that's a slightly expanded and more precise version of what we wrote down at first. So first we just said, oh, I want x close to A, and then I want f of x close to L. And let's make that a little bit more precise and agree that really that's what this is doing for me. Okay? So I want to say that you give me any positive number, which is a way of sort of measuring how close is f of x to L. And in particular, I can make that positive number very small. And so I want to say, when is it true that f of x is close to L? In other words, the absolute value of f of x minus L is less than any really small positive number you can give me. When is that true? Well, I want to actually claim that for any number you give me, no matter how small it is, I can find something in the domain, which in this picture is here. I can find an interval that's small enough. I might have to shrink it very small. But the point is, I can find an interval small enough around A so that for every single x in that interval, f of x minus L is less than epsilon. And that's going back to this picture. So just to be very clear, what is this point in the picture? This is A plus delta. This is A minus delta. Okay? That might help clear it up as well. Remember, we can always kind of use our absolute value laws to say what this means graphically. Okay? So this is A plus delta, this is A minus delta in the picture. Over here, this is L minus epsilon, and this is L plus epsilon. Okay? And so that's the there exists a delta is saying that I can find this interval such that all the x's in here mean that when I apply f to those x's, the value that I get out is always close to L. How close? Closer than epsilon. Okay. All mostly happy? Any questions on that?
Yeah, using your picture, just realize that in that statement, you say there exists a delta greater than 0.
Okay, sorry. Yeah. That's actually implied by this.
Yeah.
Well, maybe it's not fully, but okay. That's it's sort of probably how I could rephrase your objection is, you know, the first time we do it, we should be very careful and write down every single thing that's true, and then over time we'll slowly leave out little parts as long as we all agree. So just to be clear as well, delta is an element of the real numbers, and in particular, maybe that is implied to you there. So delta is not necessarily a natural number. It might be, but it's just some real positive real number, and similar in the case of epsilon. Now, I think we should do two things. I just want to write down something more, and then I think we should actually write down the negation of this statement, because that may come up.
I think we need to do a couple of examples.
Yeah, we'll do examples as well. Definitely we're doing that, don't worry. This, what do I want to, in what order are we going to do things? So, well, okay, let's do an example or two and then do the negation.
Yeah.
Maybe that's better, I agree with you. But I just want to, before we do that, I want to just kind of draw your attention to one more analogy between the sequences definition and the limits of functions definition. So aside, okay. Maybe I'll write this up here. Aside. Recall that for sequences, the presence of there exists n meant solving, or well, let's say proving, meant that practically the key step in proving limits was demonstrating, or let's say finding, critically we had to actually find this capital N, or show that it exists for some reason, like the Archimedean property, to make an inequality true. Okay? So I kind of said this early on when we were doing sequences. I was like, hey, notice that, like, practically speaking, you really have to find this capital N. You have to argue that there's this capital N that makes the whole rest of the thing work for any epsilon. Okay? So, and I'll just say, similarly, for limits of functions, there exists delta tells us that in practice, a critical step, or maybe I should say, yeah, I'll say a critical step is finding delta to make some inequality true. Okay? I mean, I really don't want that to get lost as we do some examples. The thing that makes it true is actually finding that delta. You need to find that positive number, because that's what we're claiming. We're saying, we play this game. You give me an epsilon. Now I have to really argue that no matter what epsilon you gave me, there exists this delta. That's the claim. The claim is there exists this delta such that some condition is true. And we'll have to keep looking back. What is that condition? How do I remember it? What does it mean? How do I use it practically? But really practically speaking, a lot of the time what you're searching for is that delta. Just like in the sequences, we often had to like argue that there was a capital N. And sometimes the argument was just like, oh, by the Archimedean property. Sometimes the argument was like, oh, the inequality I'm interested in is less than some other thing that I already know, which in turn guarantees me the existence of a capital N by the Archimedean property or something like that. Remember, we were always comparing to 1 over n and stuff like that. So similarly here, we're going to do stuff like that. We need to find our deltas. So a lot of the time what you're going to be doing is you're going to kind of be substituting in what is A, what is f of x, what is L, okay? And you're going to be rearranging and simplifying those inequalities, just like we did in the sequences case. And then you're going to have to argue, okay, why does there exist a delta that can somehow be rearranged to look like the thing that you want to be true? But let's see it in practice. So what example did they give you in class? Because I want to give you a different one.
X cubed.
X cubed.
Is to 8.
All right, so oh, and I guess I'm not going to write this down in the interest of time, but like, remember, we write down this formal definition, and then we're going to write down like limit x goes to a of f of x equals L as notation. So just remember that this is a notational thing. This encodes this information in the same way that we did for sequences. We could always just write down things like limit n goes to infinity of an equals some a. What did we mean by that? We meant carry out the procedure that is encoded in the definition. And then later on, what we'll do is we'll prove certain things, certain facts about these limits, and then we can feel comfortable manipulating this notation, just like we did in first year. So in first year, we were quite happy to be given a problem that said, like, you know, find limit as x goes to 1 of 2x. Okay? They would just give you that, and you'd be like, okay, I know some limit laws of what I'm allowed to do, and I would just write down what the answer is. Okay? And we'll get to that stage, and we will be allowed to do that in this course, but we want to see like why we were allowed to do all of that. And the point is really, this is not a mathematical object, this is notation encoding that mathematical statement. So that's something to just sort of keep in mind. Even when we get to the level where we're comfortable to just know that we can safely manipulate notation like this. Okay? In the same way here, this is sort of like meaningless on its own, unless I tell you what I mean by carry out this procedure. In the same way that this was, right? I kind of kept emphasizing when we're doing this is not really a mathematical, this says like in isolation, this doesn't really tell you anything. It's sort of a made up notation. But what it actually says is please carry out the procedure of finding limit n goes to infinity of the partial sums of that, right? So I just wanted to like briefly make that comment. That we're going to agree that this is notation meaning that, okay? But sort of on its own without this definition, this doesn't really mean anything, unless you tell me what this procedure tells you to do. But okay. All right, so they say to us, let's say, so question, show, using the definition, that limit as x goes to 3 of 2x is equal to 6. So this seems like overly pedantic, but on the other hand, as I sort of emphasized now, this is just actually made up notation. It doesn't mean anything unless you can prove that you can carry out this procedure. So let's say that. So really formally, kind of overly pedantic, it feels like we're going to say, I need to show, so I want to show that for all epsilon greater than 0, there exists delta such that whenever x is close to a, well, let's be careful. So I'm subbing in for a. What is my a? It's 3. Whenever x is close to 3, it has to be true that f of x, which is 2x, is close to 6. Okay. That's what I want to show. All I've done is I've subbed in for a and f of x in my definition. Okay. And this is exactly like what we did in sequences, right? We were like, okay, before we get too worried about all the stuff we have to do, let's just sub into the definition. Okay, sub in the parts that we already know. So
See, in class with that, then since in class it was x minus 2 less than delta, they just said assume it's less than 1. How, why, where?
Choose the limits to be equal to.
You just randomly.
I think we should work through that next as well. But you'll see sort of the logic of where I'm gonna explain it, and then maybe it'll match up with that. Because so again, like I could sort of write this out in sentences, and if you want me to, I can, or maybe if you want to write down what I'm saying and you think that'll help you for your studying in future, that's fine. But the point is, at this stage, we kind of need to find the delta that makes this true, that when this is true, this is true. So our hope is to kind of like manipulate this expression to look like that expression, or that expression to look like this expression, if that makes sense. That's kind of all we can work with, and perhaps they just kind of skipped ahead through those steps. See?
So multiply by 2.
Yeah, so we could multiply this one to make it look a lot like that, right? So notice that 2 times x minus 3 is equal to 2x minus 6. Okay. And and if we were kind of matching it up with that, this would be less than 2 delta. Okay, if we were just manipulating this expression. So given epsilon what should delta be? We need to show there exists a delta such that dot dot dot. Okay. Remember, our goal is to show that there exists this delta given the epsilon. Okay. So what should delta be? Basically, I want this to equal that. Okay. Yeah. So delta should just be epsilon over 2. Okay. And then we'll write it out formally and see that it really does satisfy the definition that we want to. Okay. So delta equals epsilon over 2. So we found this. Okay. We're going to argue that delta. We found a delta that makes everything work. Okay, so now let's write it out carefully and just see that it really we've succeeded in our goal. And again, this is emphasizing this whole like paragraph that I wrote that was like our goal is to find the delta. We need to find a delta, argue that that delta exists. So I'm going to write like sort of my formal proof. This is just, you could think of that as rough work. This might even suffice for a solution in some sense, but I want to write it out formally to show that we didn't miss anything. We really did satisfy the definition. Suppose we are given epsilon greater than 0. Okay. Define delta equal to epsilon over 2. Then, whenever x minus, what did we say? 3, sorry, thank you, is less than delta, we have that mod x minus 3 is less than epsilon over 2, which implies, just multiplying by 2, that 2x minus 6 is less than epsilon. Okay. And since 2x was our f of x, and 6 was our claimed limit, we've actually got the exact structure of the proof from the formal definition. So we showed that you give me any epsilon, I can always, using that epsilon, define a delta that says that whenever x satisfies this inequality for that given delta, I get this inequality involving f of x and the limit 6. Okay? And this kind of procedure is going to be totally general. If you get very difficult problems, maybe with like piecewise functions or something like that, we might need to do a little bit fancier things, but the spirit is exactly the same in every case. You have some definition, you sub in for what you know, and then we're going to have to use the existing inequalities in some way to argue the existence of a delta that makes the argument that x close to a means f of x close to L true.
Do you mind also doing an example that involves x squared?
X squared, sure.
Where you have difference of 2 squares.
Difference of 2 squares. Can I see?
Yeah, this one.
And this one.
X squared plus 3. Okay.
I'm still trying to.
And x cubed. Okay, so we'll do both of those. Okay, so can I perhaps just write them down in the upper corner here? All right, so we want to show limit. Was yours x goes to 7?
Yeah.
Okay.
Limit as x approaches 2.
Oh, sorry, 2 of x squared plus 3 equals 7. Okay, and what was this cubed one from class?
The limit as x tends to 2 of x cubed is equal to 8.
Okay, cool. All right, so did everyone have a chance to write this down?
Yeah.
So in this first one, so I'll just write it like this. This is like 1 and 2. Okay. So the first one, we're again going to write down what we needed. Want to show that for all epsilon greater than 0, there exists a delta such that x minus 2 less than delta implies that x squared plus 3 minus 7 is less than epsilon. Okay. That's the okay. So we're again going to kind of repeat the situation. So we're going to simplify that a little bit in this case, and we're going to see like how can we manipulate this into this or this into this. Okay, because we're going to be given the epsilon and we need to find the delta. And this is really all the information we have at this point. Okay, so let's see. What I want is, so I'm first going to simplify the 1. So this is like equivalent to saying that. So again, let's just also say this is all rough work. We're not going to like perfectly chain together our logical arguments. We're just going to write down inequalities and play around until we get what we want. Okay, so we have this one. Okay, and we have this one, x cubed minus 4 less than epsilon. Okay, all right, because I've just simplified that. Okay. So what I'm noticing here is we could factor this, for example. That might be one way to go. That's sort of something that jumps out at me. Let's see what other kind of things we can argue. We can always kind of like, sometimes it's useful also to just kind of expand these into their form where we remove the absolute values. Okay. So what I mean by that is like this is equivalent. This one is equivalent to saying that like x is less than 2 plus delta, yeah, less than 2 minus delta, right? And this one over here is just saying that x squared is less than 4 plus epsilon than 4 minus epsilon. Okay. So this is another way. It's sort of the idea here is kind of like quote solving for x. Okay. So I feel like if epsilon is small, I can probably just take a square root here, or maybe I could square everything in this one. Maybe that's safer. But you see how I'm kind of like trying to get one to look like the other? Does that make sense? Let's see, what is the better one that we should do? Probably squaring is better than taking square roots, but I want to take the square root. Okay, so what I'm going to say is, let's just sort of, we're still doing our rough work, we're going to say, okay, I have this. That's still true as long as epsilon's not too big to make this negative. Okay, so what I could do is now set 2 plus delta equal to this. Okay, and try solve for what is delta in terms of epsilon. Okay. Again, the idea being that we need to find delta, and we're always given the epsilon. Okay. So I don't know if this is the way they did it in class. Was this example from class? Did they do it this way? Can I see what they did, just out of curiosity? Okay, so they did do the factoring method. Okay, that's fine. Maybe we'll discuss that as well. So you did.
Do you mean that they multiplied that x minus 2 by x plus 2?
Yeah, so it's similar to what you're suggesting. So they factored this. Okay, but we'll go through that in a sec too. But sorry, I'm just going to do a little bit of rough work on the side. I recommend you don't write this down, but I just want to check, like, so I have 2 plus delta equal to square root 4 plus epsilon minus 2, then 2 minus delta is going to equal to 2 plus root 4 plus epsilon. It's going to be a little bit of a problem. Sorry? So I might want to do the factoring method. Sorry, just 30 seconds and we'll clean this up. So just to show you what's going through my mind is we might want to take this and set it equal to that and then solve for delta. Okay. And the problem is it really true if I sub in whatever delta I get for that, does it do this side of the inequality? Okay, so that's a subtlety attached to this question. And I believe there is a way to resolve it, but I just want to kind of give you the fastest way. So let's see. If we have this upper bound, so the idea here that I'm looking for is that we're going to have an upper bound and a lower bound, and then we need to pick sort of a min of those two to make both sides of the inequalities work. Okay, so let's say so let's see if we can present this in a way that doesn't confuse you too much. And actually works, more importantly. So we'd like to set 2 plus delta equals square root 4 plus epsilon according to the right-hand side inequality. Right-hand side is probably not then the thing that I want. The x less than inequality. So what I mean is I'm comparing this and this. Okay. Right? However, this doesn't give the same answer as choosing 2 minus delta equal to 4 minus epsilon using the kind of dot less than x inequality. Okay, so do you see what I'm saying there? So we kind of we wanted this to be true. We have these two different inequalities, and we want to see how do delta and epsilon relate to each other. In other words, can I always find a delta to make this one true? Okay, so I manipulate this one around a little bit, and I also remove the absolute value and manipulate this one. And in the previous example, we could just easily match up this side with that, and this side with that, and everything would be fine. But if you check carefully here, because of the square roots, really this guy, setting that equal to that would be fine. I could set 2 plus delta equal to square root 4 plus epsilon. And that's just going to mean that delta is equal to square root 4 plus epsilon minus 2. But if I sub that in on this side, I'm not going to get the same thing as this. So setting this equal to this is not equivalent to setting this equal to that. So how are we going to resolve that? Well, the point is, what we can do, this is probably a little overly fancy from what I hope to do for the first example, so we'll, yep.
I'm confused when you are putting those two. How do you know that it's strong?
How do I know that?
It's strong. Like for instance, we say that x is between minus 2 and 4. And x is between 1 and 3. You can't even say that 4 is equal to 3.
Which part are you referring to?
Like,
Are you referring to the right-hand side? Are you referring to over here or over to here?
yeah, both of these two.
Uh-huh.
Like, we are saying that 2 minus delta is equal to square root of 4 minus epsilon. So I'm confused from that inequalities. How do you conclude this?
How do I get from this to that or
From
that to
these two
this?
inequalities, yeah.
Okay, so in the previous problem, what I did is, if you go back in your notes, you'll see what I did is I just wrote out, I've got like a condition involving a delta implies some condition involving f of x. Here our f of x is x squared plus 3 and epsilon. And what we were able to do is just by looking at that inequality and looking at that inequality, we could relate the two. Like I could transform that thing in the absolute value to look exactly like that, and then I could just say how epsilon and delta relate. That's what we did in the previous example. So we're hoping to repeat that sort of strategy here. And we will be able to do it, but it gets a little bit funny, and that's what I'm trying to explain here. So all I'm doing is I'm saying I've got something in the absolute value and something in the absolute value, and can I kind of relate the two? Okay. How can I make one look like the other one? So what do? I quote solve for x. And I know how to solve for x with inequalities and absolute values. All I do is I write the thing in the absolute value has to be less than, or this has to be less than, the thing in, I added 4 to both sides, but I basically removed the absolute value on this side. And on this side, I also solved for x, okay? So now I'm hoping like, okay, I've solved for x here, I've solved for x over here, maybe I can relate epsilon and delta now, okay? So I was thinking like, okay, maybe I can just take this thing on the right that's greater than x and take this thing that's greater than x and just set them equal to each other and solve for delta, because I need to find out what delta is. Every time you're doing these problems, you're given an epsilon, you need to find out what delta is. So I'm hoping to find out delta by just saying, well, x is less than this, and x is less than this, maybe they're equal. Maybe I can just choose delta to be, something that makes these two equal, given some epsilon, okay? Now, that's my hope. It turns out in this particular problem, that's not quite enough, and we're going to see something subtle about it. But everything up to there, I hope we agree on. The next part is going to be a little bit more messy. So what I'm noticing is trying to do that, by trying to just set this equal to this, that's all fine and great for this part of the inequality, the x less than something. That's what I wrote here, to the x less than ... part of the inequality. I can make this match up with this. But I can't simultaneously, using that delta, like if I choose this to be true and I say delta is going to equal this guy minus 2, by setting these two things equal, it's not going to immediately give me that side of the inequality. So, really, like, we might have a slight problem. Okay? It wasn't as easy as the last example. So how we can resolve this is finding two deltas and then taking the minimum. But we'll explain why that works in a second. Okay, so that's what I wrote in this remark. Okay. So that little speech I gave, I wrote in this remark. Okay. So, what we're going to do is we're going to choose yeah, and I just want to make sure the inequalities actually work out. But yes, that's the idea, is that we won't independently be able to get one number that works for both. So but remember, these are inequalities. So when you're trying to sort of solve for inequalities, it's not the same as solving an equation where I need to find a unique answer. I just need to find some number that, given this, implies that. Okay. Sorry, I only have to go a little faster than this, but it's a little bit loud too. All right, so what if I set delta equal to this? Can we argue that that's gonna... Okay, so well, let's go down that path. Let's see. I hope I don't waste your time. Sorry about this. I thought this would be a simpler example. There is another way to do it. I do want to show you that. But the problem with that other way is it's very direct, and we'll discuss why it works, what they showed you in lectures. But it may feel a bit like kind of out of left field, whereas I feel like if you understand what I'm about to do, well, you'll see why it works. It'll sort of work in a more broad number of problems. But okay. So let's do this. So for the upper bound, set delta plus equal to square root 4 plus epsilon minus 2, right? Okay. For the lower bound, set delta minus equal to 2 minus square root 4 minus epsilon. Right? Yeah, and it's also messy because I have to kind of argue that these are both positive as well.
How do you know that 4 plus epsilon minus 2 is greater than 2 minus
4 plus epsilon minus 2 is greater than?
that one?
Than this one?
Yeah.
Just in general, because I'm claiming this is like an upper bound and this is a lower.
Yeah.
Remember, so these are not actually the upper bounds or lower bounds in that sense. What I'm just saying is like looking at the upper part of the inequality. Yeah. So perhaps plus and minus are misleading. Maybe we could do 1 and 2. Okay. This one's clearly greater than 0. Okay, I hope we're happy with that. It's like square root of 4 is 2, and so square root of 4 plus something positive is always going to be greater than 2. Okay? This one is greater than 0 as well, although we do run into problems if like epsilon is greater than 4. Okay? But we kind of assumed epsilon is less than 4 when we did this. Perhaps I should have done this a different way, but anyway. Just give me 1 moment. Don't write down what I'm about to write down. So, what if I just had 4 minus...
So did we just choose epsilon less than 4?
Yeah, I don't know. I'm going to be completely honest with you. This is a lot. So, like I said, it can be proven this way, but it's a lot messier than how I had hoped it would work out. So, sort of debate. I'm sort of stuck in my mind about like, should we just scrap it and go to the other way, or show you this technique? And
So
yeah,
maybe
I guess
try
we're
this
wasting.
technique and then mix it with maybe it wouldn't be as dangerous.
Yeah. Can I also see how they did your X cube example? So I want to see if they just throw like different tricks at you on every single type of polynomial that they prove, or do they give you kind of a generic method?
Nope, it was not generic, because if it was generic, I would have seen the pattern.
So I was hoping to give you a generic method here, and it just got very messy very quickly. So
So they just say the receipts and ones was this and one.
I think this is how they.
Yeah.
Even with this one.
Like 3, so because we know that if we put 3 into the subdivision, we get that 10 and that's 19, and we just is,
which is 1 and
yeah.
So
And then you carry it out.
Why is this sign?
so therefore.
And can we categorize this
Minimum.
Benjamin?
I didn't really know what's going on actually, so.
Let's see.
Maybe we don't understand this from this point.
So
Said continuously. 0 is less than 3, which is less than. This is just the function.
this is delta plus equals this, plus 19
Which is the
times
limit.
plus 19 times.
So this is just basically things to
Because of that.
this because of what? 5
Oh, since
Uh,
this is less than delta.
Yeah, since that was less than 1.
You could find
Yeah, this.
could you
Okay, perhaps that's the route we should go down.
They also choose, because in this example, they using the effect method, choose like delta script possibility. And if this is the case, then using that is of.
What if you don't know how to choose delta?
That's a good question. But there's a student asking the same question.
So yeah, it's one of those
He
ways.
says like you can choose any delta. But usually we use.
Well, I think at least for linear factors,
Yeah.
so we saw that in the previous example, like any linear factor is going to work nicely. But that's still messy in general as we go for general functions.
Yeah.
So, what we do here is,
But it makes sense. This is less than 5. X plus 2 is less than 5. So we just substitute that. X plus 2 is less than 5 times x minus 2. X minus 2 is between 1 and 3.
This whole thing is making my son miss a good
sorry. Yeah, I guess I didn't know you'd done limits already, so it came a little bit unprepared in that sense. I thought we would just struggle through this without too much trouble. Okay, so
If you just do an argument and then try this in the next situation, or maybe do you think we can?
this is not going to, I mean, this is going to be equally as messy in the next question, if not worse.
So basically, we can't use the method of trying to find delta generically.
You can, I just don't have it spelled out how to do it well for this question,
Okay.
unfortunately. I thought it would work out much easier, and I just don't have it in my head, unfortunately. And sometimes it's kind of one of those things where I think, like, after this lecture, if I sit down for 2 minutes, I can write out the argument nicely for you. Unfortunately, it's just not coming to me right now. So I have to think a little bit carefully about what to do in that case. But do you see sort of the goal of what we want to do? I know it looks really messy right now, but the goal is to kind of find a delta so that we can get the upper inequality to be true and the lower inequality to be true simultaneously, in the same way that we had to do with sequences when we needed to like make two sort of bounds true. So I want to say, but I just don't see the last step in the argument, which is why I haven't written anything more. So what I would, my sort of guess here is what you'd say is like, okay, let's take the minimum of these two deltas, argue why it's not a problem that epsilon is less than 4, which actually is a problem. But okay, we could probably resolve that separately, and go from there. The other way I was looking at, just to show you, I think I may as well erase this because I don't know. Like, okay, so the other way I was going to show you, try and investigate, maybe something will just pop out. So perhaps where we're going wrong is trying to manipulate this with the square roots. Maybe what we should be doing is manipulating that to look like that. So we can say that if I just square everything in this inequality, I have 4 minus 4 delta plus delta squared is less than x squared is less than kind of 4 plus 4 delta plus delta squared. And then we could say something like, well, can I match this up to 4 plus epsilon? And can I match this one up to 4 minus epsilon in some reasonable way? Right? And now we can avoid the whole square roots and conditions on epsilon and things like that. And so this one would imply that delta squared plus 4 delta is equal to epsilon, and the question is, can you always pick the delta to make that true? And then over here, this one implies that, sort of, let's write it this way, implies that kind of epsilon equals to minus delta squared plus 4 delta. Okay. And can we kind of satisfy both of these in some reasonable way? Did I do that right? Yep. We're seeing.
Those to be true, doesn't negative delta squared have to be equal to delta squared as well then?
So this is where the kind of min argument comes in. So you could have kind of like a delta 1 that makes this condition true and a delta 2 that makes that condition true, and then try to take the min and see if you can get everything kind of, and then put it all together logically. So this one's funny because of that being negative. So.
And since this delta greater than 0, right?
Yep.
Oh, okay.
So can I just ask, like, do we solve these equations simultaneously?
What do you mean by simultaneous? Oh, you mean just like
So
two very. So these I think will just be straight up. will they be inconsistent? I think you just find out that like delta squared is 0 if you try to solve them simultaneously. So no. If you could, you'd be
Those
done.
two things, you have negative delta squared is equal to delta squared. Because the 4 delta will cancel with that 4 delta over there, and then you're left with negative delta squared is equal to delta squared. Oh no, how are you going to prove that? Because you can't take the square root of one side and be free. You see, that's weird. Then you get negative delta is equal to delta, but delta is positive, so it's, you're right, I think.
Yeah. Okay, so maybe we just talk through the method from class, and I'll try to resolve this on my own. Because it's too messy. Okay, so we'll go back. But you can see it's not immediately straightforward. It probably actually is immediately straightforward, but unfortunately, like I said, I don't have the argument for you, so I'm sorry about that. All right, so what we're going to do is we're going to say, notice that x squared minus 4 less than epsilon is equivalent to saying that mod x plus 4 mod x minus 4 is less than epsilon. Right, so there I'm just factoring this. Okay, so this is what they showed you in class, right? And then the question is, can you kind of find a delta that will bound both of these factors to be less than epsilon? Sorry, thank you, that's critical. So the x minus 2 factor is very nice, because that actually just shows up over there. Okay, and then the only thing we have to worry about is the x plus 2 factor. Okay? So I'll just sort of remark the x minus 2 factor appears in the inequality involving delta. So we need to deal with the x plus 2 factor. And really what would be nice is if we could have less than 1. That's probably not going to work.
Yeah, and you said like this one. You said x, because the absolute value of x plus 2 is distance from x to minus 2, which is probably approximately to 4.
Sure. Is approximately 2, 4?
Yes.
You mean when you of x squared is approximately?
Yeah. I think.
I see. Oh, I see what you're saying. Okay, so you're saying like x is close to. We're looking at the limit as x goes to 2.
Yeah.
So the distance from x to minus 2 is probably about 4.
Yes.
Okay. So we're hoping to bound this by like what, 5? Or?
Something like that. Yes, exactly.
Okay, so I guess I'll just copy that remark. So did you follow what he said? Okay, so then we'd say, so now we need to treat the mod x plus 2 factor. Okay, notice mod x plus 2 describes the distance from x to minus 2. Okay, do we all agree on that? Because I could write this as x minus minus 2. And since we're asked to consider.
Sorry. So when you say it describes the distance from x to minus 2, is it like, are you saying like similarly x to 2? Because that's what I thought x to.
No, so you have something like a minus b
Yeah.
equals distance a to b.
Okay, and then x.
For any number a or b, whether they're positive or negative.
Yeah.
Okay, so I'm going to write x plus 2 is equal to x minus minus 2.
Oh,
Like that.
so it's not the same as the distance from x to 2. It's only a distance from x to negative 2.
Yeah, this is for any a and b, positive or negative or 0, but I have to have that minus sign. So I'm going to look at this and say, okay, I get my minus minus 2. Is that cool? And if you go, and I mean, like, I could say it another way. You could kind of say, like, okay, no, I'm just going to leave it there. Yeah. And since we're asked to consider the limit as x goes to 2 of f of x, since we're asked to consider the limit as x goes to 2 of f of x, x near 2 means distance from x to minus 2 is about 4. Okay? Right? Because if we're looking at x near 2, what is the distance from 2 to minus 2? And the number line, the length of that is 4. Right? So in our, just to draw you a picture, in our problem, they're asking us to investigate the situation when x is somewhere near 2. This is what limit x goes to 2 is saying. It's like, please look at x when x is near 2. Okay? We were rearranging our inequalities and trying to rearrange our definition to do something useful. We found that the x near 2 factor appeared, the x minus 2 factor appeared. But we also had this other factor that was kind of weird, x plus 2. So we're just making a remark. We're like, what does x plus 2 in absolute value mean? It means that this is the distance from x to minus 2. That's just what this object is. It's the distance from x to minus 2. Yeah.
Just have a thought now.
Yeah.
We can, running away from all these argument altitudes and a delta, we can just simply use that fact with this fact. Like, because the distance from x to plus 2 is approximately to 4, and I've computed a delta in terms of epsilon in the previous method, and I found this was 1/4 epsilon. Sorry?
Using those two inequalities we added both these equations together, and you got this.
And look at that, 1/4.
But did we have, maybe it's right, but didn't we agree that those two equations were inconsistent? So what happened?
Because then we had this thing, delta squared plus 4 delta is equal to epsilon.
That was the
Then we
right-hand
have-
side, yeah?
Yes, then we have negative delta squared plus 4 delta is equals.
Absolutely.
Yes. And then he just added these things together instead of equating.
You know, like it is written like this. This one will cancel, this one will make 8, this one will make -2, then I have this. And using this argument,
I agree with you. That's probably what we needed. I'm just really struggling to reconcile how we can get two different answers in two different ways. Go.
You need to.
because now I think we've solved the problem. Because we can from those two inequalities, like the absolute value of x plus 2 times the absolute value of x minus 2, and which is going to be less than, as we said, the absolute value of x plus 2 is approximately 4. We just said that now. 4 times this. This delta.
Well, so we want to stay away from saying approximately 4. We want to sort of bound it by something bigger. But I get what you're saying. I get what you're saying. Maybe that's why this. I'm still like a little bit concerned here.
I don't understand how it worked out with it doesn't work out with the two.
Okay, you can proceed to take up like this. Yeah.
Okay, yeah, that's maybe not a bad. But that's good. That's really smart. I'm just like, yeah, okay. We'll talk about it at the end. So perhaps the other method can be repaired. But anyway, that was my goal. I said I would hopefully send you a Boolean announcement and next time give you a better thing. So we're trying to bound this quantity by epsilon, and we're saying we want to find a delta that makes this quantity bounded by epsilon. And we feel pretty confident that we can handle the x minus 2 part, because the x minus 2 part is the part that needs to be less than delta right in the start. So this other x plus 2 part is a little bit more foreign, and we're like, what should I do with that? So we write out this remark. We're like, what does x plus 2 in absolute values, what does that mean? It describes the distance from x to minus 2. So since in this question we're caring about x near 2, we're expecting the distance from x to minus 2 to be about 4. So maybe we can obtain an inequality of this form, x plus 2 less than, say, 5, okay? I'm just picking a number a bit bigger than 4. Okay. I want to talk about x near 2, so I'm hoping that means that x plus 2 is sort of less than, in absolute value, is less than 5.
5, I'm so sorry, that went way over my head.
So if x was literally at 2, sorry,
Yeah.
if x was literally at 2,
Yeah.
then mod x 2 plus 2 would be equal to 4. But we're not looking at x at 2, we're looking at x near 2. Okay? So we're sort of saying, okay, if I go close to 2, sort of like this, if this was 2, what might be true in terms of an inequality? And it's like, maybe this is true. If we're close enough to 2, we're saying that x is sort of a bit less than distance 5 from negative 2. So here's 0, here's negative 2. The exact distance is 4, but maybe if x is nearby, maybe it's a little bit bigger, a little smaller, maybe it's a little bit bigger. Hopefully it's at least distance less than 5. That would be the distance 5.
Mm-hmm.
So maybe x is less than distance 5.
Okay.
So can you just ask, like, why can't you prove that x plus 2 using some information you know about x?
Do you have a suggestion?
I have a suggestion, which is
Okay.
in this way. So, which all converges to like choosing a delta.
Okay, good, yeah.
Yeah.
That's
So
good.
so we know that an absolute value of x, choose delta to be 1. Right. Therefore, the absolute value of x minus 2 is less than 1. If we choose.
Okay, so you're saying let me just pick delta to be 1.
Yes.
Okay.
Then the absolute value of x minus 2 is 1, and which means that the absolute value of x is bounded from 1 to 3. You can do that.
Yeah.
Yes, and then at 2, and we reach, which is going to be 3, and 5, which satisfy this condition,
Uh-huh.
then we have this condition. We can obtain it.
So let me just write down, okay, so again, I would suggest don't necessarily write this down, but let me just write down your argument. So you're sort of saying you have two pieces. You have like, you want delta equals 1 implies sort of